Okay. Can everyone see my slides?
Yep, looks good.
Yes, we can.
Okay, thank you. Okay, so sorry, I've got some things covering my slides here. Hold on. Maybe you can't see that. Okay, so I'm going to talk about the Muon g-2 experiment here at Fermilab. A little bit about the past, the history of g-2, a little bit about what's been going on or what is going on currently with the Muon g-2 experiment at Fermilab, and then a bit about the future, where we're going. And I'll also talk about a little bit about the computing side of things and OSG's role in that. So I know not everyone is a particle physicist, so I want to bring people up to speed on exactly, just what the muon is. So it was first observed in 1936 by two scientists at Caltech when they were actually looking at electrons, the energy loss of electrons in cosmic ray showers, and using a cloud chamber. And what they observed were not only the electrons, but also these additional, what they call penetrating particles. And they concluded that there must be additional particles of unit charge, meaning that of an electron, but with mass larger than that of a normal electron, but smaller than that of a proton. And then there's a lot of history that between that discovery and now, but I don't really have time to go into it, but I want to let you know where we are now with the muon. And that is that, it's an elementary particle. In other words, it doesn't have any substructure. It's a lepton, so meaning it doesn't interact via the strong force, which is the force that holds atoms together. It's charged. It has a charge equal to that of the electron. I'm sorry, this equation you're seeing here is shifted. It has an antiparticle, which is called the anti-muon, which is actually what we work with, what we use at Fermilab, and that's positively charged. It has a mean lifetime of about 2.2 microseconds. And then it decays after that to an electron neutrino and an anti-muon neutrino. And the lifetime of the muon is one of the things that makes it so useful for doing experiments in trying to understand what's going on with the standard model. It has a spin 1/2. Spin is an intrinsic angular momentum, so you can imagine it kind of like a little top, but it's, as we know, it doesn't take up any space, so you don't want to be thinking about it like a top in that way. And that means it's a fermion. And the most important thing to take away from this at this point for this talk is that if you have a particle with charge and spin, then it also has what we call an intrinsic magnetic moment. So in other words, it acts like a little small dipole magnet. So the muon is very much like the electron, but 207 times heavier than the electron with a mass of 106 MeV. So just a brief discussion here about angular momentum and magnetic moment. So if you have a charged particle moving with an orbital angular momentum, so that would be like a particle moving around, say, a nucleus or something, and it has a magnetic moment given by the expression Q, which is Coulomb's constant, E, which is just the charge of the electron, over 2m times the vector orbital angular momentum. So a charged particle that has spin angular momentum also has a magnetic moment, which is given by the same expression with a G multiplier out front. And G is what we call the G factor of the particle, and it's particle dependent. It is a unitless number. And notice that if the charge of the particle is negative, as is the case for an electron or a muon, then the spin and the magnetic moment are anti-parallel. For the electron, the G factor has been measured. I'm not giving all the significant figures here, but you'll notice it's 2 plus about 1,000% or so, 1,000th of a percent, sorry. And the corrections to the value of 2 are those corrections that come from quantum field theory. The factor of 2 itself comes from the fact that the electron is a quantum particle. That's predicted by the Dirac equation. So if we define the difference between G and 2 over a factor of 2 as the anomalous magnetic moment, then we kind of capture everything that is outside of this, beyond the plus sign after the 1 in that expression above. So that's everything that comes from quantum field theory. So there we go. So for a muon, it also has quantum corrections to its G factor. And I'm listing the first several, I guess the first 5 digits of those there. And we can think about those in terms of the physics, that we know right now. I'll call it, that's the standard model of particle physics. And we can write the G factor of the muon in terms of these various quantities from different parts of physics, different types of physics. So the standard model value has a contribution from QED, which is quantum electrodynamics, that involves photons and leptons. It has a contribution from electroweak physics, so that's the physics involving the W and the Z bosons and the Higgs boson, and also it has a contribution from hadrons. In other words, the hadrons are the particles that interact via the strong force, so quarks and gluons. Okay, sorry. So thinking in terms of Feynman diagrams, which is one way the particle physicists like to think about their physical processes. You have QED. For some reason, I'm sorry, my pointer isn't working. I don't know, but so I can't really point at anything. We have a QED correction or QED corrections. You're looking at the first order loop correction. We have electroweak corrections, and we have hadronic corrections. And I'm showing the hadronic light by light correction and the vacuum polarization corrections. And you can add up these corrections to an infinite number of loops. And obviously, the more loops you add to your calculation, the more precise your calculation is. The QED and electroweak contributions can be precisely, relatively precisely calculated. If you look in the chart I gave you there, you can see the contribution to the anomalous magnetic moment from each different type of physics, and you can also see in the blue. You can also see the relative uncertainty in the orange. So you'll notice that the hadronic components are contributing largely to the uncertainty in the muon anomalous magnetic moment. So what can we learn from the anomalous magnetic moment? So obviously, if we do better calculations of, in particular, the hadronic part, and we make better measurements of a mu, we can get a better understanding of the other underlying physics. Does the standard model tell the whole story, or is it an incomplete picture? If there's some disagreement, then the standard model clearly, is not the whole picture. And we can determine, depending on the level of discrepancy, at what energies the new physics would come in to play. Why do we use the muon and not the electron, say? That's a question that many people ask. So a lot of the new physics interactions are proportional to the mass squared, actually to the mass squared over the energy squared of the new physics. And the muon, because it's so much, as I said, 207 times more massive than the electron, the new physics is, about 40,000 times, the muon's about 40,000 times more sensitive to the new physics. So, so that's the reason we don't use the electron, we use the muon. And you might say, well, then why don't we use the heavier cousin, the tau? And unfortunately, the tau lifetime is way too short. It's order of picoseconds, and we can't, we just can't measure anything on that scale of time. So the first measurements of the anomalous magnetic moment of the muon date back to the 60s at CERN. And over their 3 experimental campaigns, they improved their precision from 4,300 parts per million to 10 parts per million. And those results were all considered to be in agreement with the standard model. However, the E821 experiment at Brookhaven also did measurements of g-2, and they reported a slight tension with the predictions. So if you take a look at the plot on the left here, you can see the this doesn't show all the, it doesn't show all 3 of the CERN values or measurements here, but you can see 2 of the CERN measurements, one using muons and one using anti-muons. And then you can see the 4 BNL, Brookhaven measurements that use muons there, and then the average. And you can see that over time, the result of the measurement has become, slightly in tension with the standard model theory. So just to show you, I thought that the the table on the right was an interesting table, so you could see the incredible increase in precision over the years, starting with the first CERN experiment in 1961. Their precision was 4,300 ppm, and ending in the last BNL measurement using actually muons, and their precision for that one was 0.72 parts per million, and when you put it all together, you get 0.54 parts per million. And at the end of that, so the status basically as of before April of last year was that there was some tension between the average and the standard model value in giving a discrepancy of about, a little more than 3.5 sigma. That sounds like a lot, but in the particle physics world, we need a 5 sigma discrepancy for discovery. So you can imagine that for, since the early 2000s, this has been something that that has been on the mind of physicists. So the question then, might be, well, how do you actually measure, how do you measure the anomalous magnetic moment? So I'm sure everyone's familiar with a spinning top. When it has a gravitational torque on it, it precesses, which is what you see in the upper video there. And similarly, a particle with a magnetic moment also precesses when it experiences a torque, but this time we're talking about a torque from a magnetic field. So if you apply in this picture, if you have a vertical magnetic field and the spin is slightly off kilter there, I'm sorry, if the magnetic moment is slightly off kilter, then you'll know then that magnetic moment itself will precess. So we understand the physics of the precession, and since it's related to the magnetic moment, we take advantage of that. So you can imagine injecting a beam of polarized muons, polarized meaning their spins are all aligned and in the same direction. Obviously, that's not something you could do on perfectly, but more or less polarized. And you you inject those into a region that has a uniform magnetic field, then those muons will precess, and eventually they will decay, right? Because they have a lifetime of 2.2 microseconds. And then it turns out that parity violation in the muon decay results in the highest energy decay electrons preferentially having their spins lined up with their momentum. So if we can measure their momentum, then we can, know which way they're, we can, in a sense, observe the precession. So this, here I'm trying to illustrate in this figure here, what the situation would look like without the g-2 anomaly. In other words, if you had no quantum field theory contributions, if you put a momentum, a muon in a or charged particle in a circular orbit in a magnetic field, constant magnetic field, there's some very complicated equations of motion that come with this. But if the muons have a momentum that we call the magic momentum, then the spin precession and the momentum the spin and the momentum will line up. In other words, the spin precesses at the same rate as the momentum rotates around as it goes around in a circle. And the magic momentum is there. Sorry, I don't know why I'm having problems with speaking. The magic momentum, let me get it right, is there to cancel the effect from the electric field that is in the more complicated equation. So now if we have, we do consider what the situation looks like with the anomaly. So in other words, G is not equal to 2 in this case, then the spin and the momentum do not continue, they don't stay together, and you get what we call the anomalous precession frequency of the spin, and that's given by the omega A Q over M A mu, which is the the part of G that we want to measure, times the magnetic field. So if you can measure the magnetic field, and you can measure the anomalous precession frequency, then you can obviously determine what the anomalous magnetic moment is. So so as I said, sorry, as I lost my cursor again. As I said, so you can measure the magnetic field, and you using, say, the proton Larmor frequency, and we do that with NMR probes. So if you take the expression on the inside the circle there, the omega A, and you plug in what you know about the magnetic field, then you get the expression in the box on the right, which is, you can see that the anomalous magnetic moment, excuse me, is measured in terms of the two frequencies, the anomalous precession frequency, which is something we're going to determine experimentally, and then the proton Larmor frequency, which we can also measure. So I put these in here because I wanted, I wanted people to have a reference if they were interested in learning more about some of these other pieces in the expression, but we don't really have time to talk about it today. So the Muon G-2 collaboration at Fermilab consists of, it's actually over 200 collaborators now, this is a little bit off, 35 institutions in 7 countries. sorry, I keep seeing things on my screen. Okay. So the idea was to reuse as much as BNL from the Brookhaven experiment, as possible, but to improve things that, sources of uncertainties, systematic uncertainties, etc., that were recognized in that experiment. So the experiment at Fermilab reuses the storage ring magnet and the superconducting inflector. It uses a refurbished NMR trolley and magnetic field measurement system. It has a pure muon beam with no hadrotic components. Some things are just improvements here. It's got a segmented calorimeters, and these allow observation of the minimizing ionizing particles such as muons that are lost from the storage ring. It has a new fast kicker. It has improved magnetic shimming, which has improved the magnetic field uniformity by a factor of 2. It's got 2 straw tracker arrays upstream of 2 of the calorimeters, which allows tracking. It has a more rapid rate of filling the storage ring. So the goals of the experiment at Fermilab were to accumulate 21 times more data than BNL. So you can see the statistical uncertainty at BNL was 460 parts per million, and parts per billion, and at Fermilab the goal is 100. And in order to do that, we have to have 21 times more data. We want to improve the systematic errors by a factor of 3, from 210 to 70 parts per billion, and then improve the overall uncertainty by a factor of 4. So that's the goal. As I said up here, so we reuse the storage ring magnet and the superconducting inflector from BNL. So in 2013, the magnet, the storage ring, had to be moved from BNL to FNAL, and it took several weeks in June and July. It started, it came by boat, actually by barge, down the east coast of the United States, up the Mississippi. And then it was unloaded over by ANL, and then they trucked it from over the interstates to Fermilab, and I-88 itself was closed for several hours on one morning. I think perhaps my favorite stop of this was when I got to see the ring before it got to Fermilab. It was parked in a Costco parking lot near Argonne for a day, between Argonne and Fermilab. So lots of people, G-2 people were there answering questions. This was before I was a member of the collaboration. Some colleagues and I from Argonne went to look at it. And here you see it being hauled into Fermilab, and of course there was a big celebration. And the picture on the right, it was this. This is not a doctored picture. It's just an amazing cloud formation. Storm came in after the ring had been delivered to the lab, and there's this amazing picture that you'll see everywhere. So the Fermilab Muon campus I'm showing here. You can see the proton. I really wish that my cursor was working, sorry. So you can see where the protons are stored in the recycler ring, and then they come and hit the muon, the target station for G-2. And then down in the, and then, the muons themselves are stored in the delivery ring there, and then the batches are injected into the building MC1, which you can also see a picture of here on the left. So what does the life of a muon in the G-2 experiment look like? So, over on the left, we start with protons from the accelerator complex. They hit a target. Pions are created. Those pions decay to muons. As we know, the muons, they're tiny magnets, and they spin just, like tops. And then those muons are fed into the uniform donut-shaped magnetic field. And after each circle that they make, the axis, spin axis, changes by 12 degrees, but it keeps traveling around the circle. After circling the ring many times, the muons decay to electrons or anti-electrons and neutrinos, and they decay preferentially in the direction of the muon spin for the highest energy electrons. And then one of the 24 detectors sees the electron giving the muon spin direction. So to be a little bit more less cartoonish, here we see the storage ring. You have a polarized, in this case, we're using anti-muons, injected into the storage ring at that magic momentum. And then we have a superconducting inflector magnet, which cancels the main focusing magnet. So obviously the ring has a magnet in it to make the, excuse me, keep the muons going around in a circle, but you don't want them, you can't have any magnetic field in the injection region there.
Hey, Lisa, 2 minutes for wrapping up.
Sorry, 2 minutes?
Yes.
Okay, got it. All right, and then the muons then experience a kick into the proper orbit. There are electrostatic quadrupoles that focus the beam vertically. And then ultimately the muons decay into positrons, and those positrons, do the magnetic field curl into the calorimeters and where they are detected. So the result you'll see is this wiggle plot, we call it. This is the number of detected positrons as a function of time over the fill. And so the detected positron, the time spectrum here, again for certain positrons of a certain energy, is oscillating with the spin precession frequency omega A. So we measure omega A by fitting this curve.
Lisa, you're muted.
You managed to mute yourself, Lisa.
There we go. Sorry. I think maybe that was where my cursor had sat because I didn't push any buttons. Okay, you guys can hear me okay now?
Yeah, we can hear you.
Yeah, sorry about that. Okay, back to play. Okay, I still can't find my cursor, but the spin precession frequency is can be obtained by fitting this curve. This is the very simple 5-parameter fit. It obviously is much more complicated, but we don't need to go into that. And then the omega A is inserted into the equation that we talked about earlier in order to get the anomaly. So the results from the run 1 of the Fermilab experiment are shown here. The Brookhaven result is shown in the blue. The Fermilab result is shown in the red. And you can see here that, I'm sorry, there's, for some reason, my equation isn't showing up. My value for the Fermilab result, it is in my, okay, I don't know, maybe the screen sharing is causing a problem. Yeah, sorry. The average, if you average the results from Brookhaven and Fermilab experiments, you can see the result down there at the bottom. So 116,592,061 with uncertainty of 41 in the last 2 digits, and so that's a 0.355 parts per million measurement. You can see the standard model prediction, the most current standard model prediction way over to the right. Oh, there it is. I'm sorry. So that was just a mistake. on my part. Just to give you a sense, the Brookhaven result is about 3.7 sigma off the standard model prediction. Fermilab is about 3.3 sigma off the standard model prediction. And the average of both experiments is 4.2. So not yet our 5 sigma result that we would need to claim discovery. Great things that came out of the run 1 analysis. There were 4 analysis publications. I encourage you to check those out. The question is, where to next? So our goals in general are the best measurement of muon g-2. Our target is 140 parts per billion. We want to confirm or refute the deviation seen at Brookhaven. So that is, 4 times improvement over their sensitivity, which was 450 parts per billion. And we want to have the best measurements for both positive and negative muons. So we have a target of 5 times the improvement over BNL for positive muons, which is what we're running now, and then a 2 times improvement for negative muons, which we hope to be running in the not too distant future. So you can see this is our number of positrons that we've collected in terms of BNLs. So we had about twice the number of positrons after just as BNL to just run 1, and we're heading up towards our goal is 15. So our goal is about 16 or so. Right now we're at 15.62. That the run 1 results were released last April. That was only about 6% of the target stats. The results from runs 2 and 3 will be released next winter sometime. Run 3 itself has 3.3 BNLs, and then results from runs 4 and 5 should be released in 2024. And I just want to give you a very quick insight into the computing side of things. So for raw data, you can see we have, we're looking at run 1 was, excuse me, 0.4 of a petabyte. Run 4 was 2 petabytes of raw data. Run 5 will be similar to that. Sorry. For process data, we're looking at, around for run 4, about 94 terabytes of data. This is a plot of the picture in the center here is a picture showing a production grid usage. So we have reserve quota of 5,000 grid slots, which are shared by all users. You can see that we, occasionally, depending on what's going on, if there's a publication coming or something, or a collaboration meeting, we have spikes. And then I just wanted to show you some of the pictures of the usage. So in the upper right hand corner, we have monthly wall time. This is from the time when g-2 started computing. And we have since that time, 17% of the production work has been run at offsite computing resources, and about 10% of the analysis of work has been. And I should say that I expect that in the future, we will be running more jobs offsite as we have to deal with just more data. So in summary, the Muon g-2 experiment at Fermilab released a 4.2 sigma result, discrepancy result in April of 2021 of the Muon Anomalous Magnetic Moment. It confirmed the BNL measurement, which was made almost 20 years ago. We have much more data to analyze. That was based on only about 6% of the total data we hope to collect. And the OSG resources have and will continue to play an important role. Okay, that's it.